section 4.1. Is it me? Oh, crap. You're not supposed to see that. All right, section. Now everybody who watches that video is going to hear you guys laugh. All right, section 4.1 is on maximum and minimum values. That's the title. Okay. So this first part is learning how to find the absolute maximum value of a function, absolute minimum value, and then we'll talk about how to find the local minimums and the local maximums. Okay. So let's start off with a definition from your textbook. And so C is a number in the domain D of the function f. Then the value of the function x equals c, f of c, is the absolute maximum of the function on the domain if f of c is greater than or equal to f of x for all x in the domain D. Okay? So f of c is the absolute maximum, okay, if it's the largest function value over the domain D of the function. Okay. Nico, are both those light switches turned on? Yes. Okay. Because we're not using the overhead today. So we could, so apparently this light doesn't work. All right, and then we have the absolute minimum value. So f of c is the absolute minimum value of the function on the domain if f of c is less than or equal to f of x for all values of x in the domain. Okay, in the domain D. Okay. So let's demonstrate this. With the graphs of some functions. So here's my coordinate plane, and all of these I'm going to draw in the first quadrant without loss of generality. So here's the graph of a function, and it starts here at the point 2, 3. X is equal to 2, y is equal to 3. And it ends over here at the point 10, 15. X is equal to 10, y is equal to 15. Okay. The domain of this function, right, which is the x values go from 2 to 10, right? So in interval notation, right, bracket 2, comma 10 bracket, and in inequality notation, x is greater than or equal to 2 and less than or equal to 10. The range are the y coordinates, and the smallest y coordinate is 3, and the largest y coordinate is 15. So the range goes from 3 to 15. Well, the value of the function x equals 2. Right, so remember, this is the graph of f of x, right? Some arbitrary function. And you can see that the value of the function x equals 2 is 3. And 3 is the smallest y coordinate, right? So the smallest y coordinate, right, is the absolute minimum value of the function on the domain. So f of 2 equals 3 is the absolute minimum value of f on this domain, right, from x equals 2 to 3, x equals 2 to 10. Okay. So the absolute minimum value, right, is the minimum y coordinate. Right, that's the minimum function value on the domain. Okay. And you can see that at x equals 10, right, f of 10 is equal to 15. That's the 15 is the largest y coordinate. That's the largest function value, and so f of 10 equals 15 is the absolute maximum value of f of x. Okay, and so found that from the maximum y coordinate. Okay. So the minimum y coordinate is the minimum value of the function, and the maximum y coordinate is the maximum value of the function. Okay. All right, so let me redraw that graph with a small difference. So here we have the x, y coordinate plane. And it starts at x equals 2 and ends at x equals 10. But instead of a closed circle here, we have an open circle. And instead of a closed circle up here, we have an open circle. And the location of that open circle, right, here is at point 2, 3. And the location of this open circle is at the point 10, 15. So the domain, remember, open circle means you don't include the point, right? So the domain is the open interval from 2 to 10. Okay? And inequality notation, right, the x values are greater than 2 and strictly less than 10. And the range, okay, is the open interval from 3 to 15. The y values are greater than 3 and strictly less than 15. In that situation, there's no absolute maximum or absolute minimum. There's no maximum y coordinate, and there's no minimum y coordinate. Okay. In this case, there's no absolute maximum value or minimum value Now, if you take more advanced mathematics, do you think they wait till I'm lecturing to do that?
Yep.
You take more advanced mathematics, they'll talk about least upper bound and maximum lower bound, things like that, infimum, supremum. But there's no number that we can peg. There's no real number we can say, hey, that's the absolute maximum value of the function. Because whatever number you give me less than 15, I can find a number greater than that, but less than 15. Okay. And same with the minimum.
Mr. Bell.
Yes, sir.
So every time there's an open circle, it'll be parentheses and not marker.
Yes. Yes. Right? Yeah, this is interval notation. When there's an open circle, you have parentheses. When you have a closed circle, you have brackets. Okay? All right, let's draw one more graph. And draw our friend the parabola. So here's the vertex of the parabola at the point 3,5. Okay. The graph of quadratic function is a parabola. Okay. And what's the domain of all quadratic functions? All real numbers. Now, you may, as this goes up, but you go out here to minus 1,000 on the x-axis, there's actually a value of the function. Okay. But it's way, the graph is way up there. So, the x values, the x coordinates, is all real numbers. The range, what's the range for this quadratic function?
5 to infinity.
There you go, 5 to infinity. The y coordinates go from 5 to infinity. Does this function have an absolute minimum? Does it? Katie? Horton?
I don't know.
Connor? What's the absolute minimum value of the function? 5. That's the smallest y coordinate, right? The range goes from 5 to infinity. The smallest y coordinate is 5. Okay? So, f of 3 equal to 5, okay, is the absolute minimum value of the function. Okay. So I keep forgetting to write this, but right, this is the graph of y equals f of x. Does this function have an absolute maximum value? Nico? No? Why? It goes up forever, right? There's no maximum y coordinate, so there's no maximum function value, right? So this function has no absolute maximum. Okay? So now, when I release the homework, hopefully later today, you'll be able to do all the problems where you find absolute minimum, absolute maximum.
Say that parabola had like a bump in it, like a hump, and there were two.
A hump.
Yeah, like, my question is, can you have like more than?
You mean like a polynomial?
Yeah.
Alright, so you want me to draw a polynomial? I mean, this is sort of a polynomial
I
part
was
of
just wondering, like, can you have more than? Can you have like two absolute minimums or two absolute maximums?
Well, you can have the same absolute minimum at two different locations. Okay? So you're asking a very good question. Okay? So let's say, right, I have, and I'm going to do my best to get the height the same. Okay? Well, let's say I got this graph of this function. Okay? And so this is like the point 5, 1, and this is the point 10, 1. Okay? The minimum value of the function is 1, and it's located at two different points, right, on the graph. So you can have that situation. Because all we're asking is what's the minimum value of the function. We're not asking where is it located. Okay? So that's a good question. Okay. All right. Any others before we move on? Okay. So now let's talk about local maximum, local minimums. So definition 4.1.2 from your textbook. The number f of c is a local maximum value of f if the function values at c are greater than or equal to all the function values near c, when x is near c. So in math they call that a neighborhood. Okay. The number f of c is a local minimum value of f, local maximum value of f, if f of c is greater than or equal to, sorry. Local minimum value of f if the function value at x equals c is less than or equal to f of x when x is near c. So let's demonstrate this with some graphs. So again, I'm going to draw the graphs in the first quadrant. So this is a graph of y equals f of x. And this is a graph of a polynomial function for all values of x. Okay? So this one's not getting cut off on the left end or the right end. Okay? Now, the local minimums and local maximums are at the top of the hills and at the bottom of the hills. So the local maximums are at the top of the hills, and the local minimums are at the bottom of the hills. So we'll label this one A, this one B, and this one C. Those points, A, B, and C, for those of you who took pre-calculus here, are called turning points. Okay? Because as you go from left to right, you're going uphill till you get to the top of the hill, and then you're going downhill, right? So that makes A, so when you're going from uphill to downhill, that makes A a turning point. B is a turning point because you go from going downhill to uphill. And C is a turning point because you go from going uphill to downhill. Okay? So in pre-calculus and algebra, right? College algebra, those are called turning points. Okay? In calculus, they're called local extrema. A, B, and C are called local extrema in calculus. The tops of hills are local maximums. The bottoms of hills are local minimums. Okay? So in this graph, A and C are local maximums. And B is the local minimum. What can we say, what else can we say about the point C? Say what?
The absolute max.
It's also the absolute maximum, right? It's the highest point on the graph, right? That's the largest y coordinate. So C is a local and absolute maximum. Okay. What about point B? Is it an absolute minimum? No, because the graph goes down forever on both ends. There's no minimum y coordinate, right? The range, right, minus infinity to whatever the y coordinate is at C. Yeah. Okay. Very good. All right, so let's draw one more. And so this is the point 210. This is the point 53. And this is the point 87. Okay. Does this function have an absolute maximum? What is it? 10, right? F of 2 equal to 10, right, is the absolute maximum value of the function f. Okay. So again, this is the graph of y equals f of x. Does this function have an absolute minimum? No, because it goes down forever. There's no minimum y coordinate, right? So no absolute minimum. Does this function have a local maximum value? Yes. What's its value?
8, 7.
It's 7, right? This isn't really a hill, it's like a mountaintop, but it's the top of a mountaintop, right? So this is the local maximum, okay? And so the value of the function, right, is 7. So f of 8 equal to 7, okay, is the local maximum value of f, okay? Does this function have a local minimum value? What is it, McKenna?
F of 5, which is 3.
Yeah, f of 5 equal to 3 is the local minimum value. Right? F of 5 equal to 3 is the local minimum value. Okay? So over here in my graph on the right, that's basically a graph of polynomial, and they're nice smooth curves. But also mountaintops and mountain valleys, right, are also turning points, the location of local maximums, local minimums. Okay. Any questions on that? Okay. So now you know how to find the local maximums, local minimums of a function on the WebAssign holder. All right, so let's talk now about what the textbook calls the extreme value theorem. And it says if the function f is continuous, we know what continuous means, right? If f is continuous on a closed interval from A to B, okay? So this means for x greater than or equal to A and less than or equal to B, right? We're using interval notation. Okay. Then the function f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some numbers c and d in the closed interval from A to B. So let's demonstrate that with a graph. Okay. Remember, f of x is continuous on the closed interval from a to b. So again, we draw this in the first quadrant. And so our graph starts here at x equals a, and it ends here at x equals b. Okay. And since it's continuous, so starting here at x equals a, I can trace out the graph, without lifting my finger off the board. Okay. So what the extreme value theorem says, well, if this thing is continuous from x equals a to b, there's got to be a point on the graph where the function attains its maximum value, and there's got to be a point on the graph where the function attains its minimum value. Okay. So this is the point x equals c, and so this is the point c, comma, f of c. This is the point x equals d, and so the minimum value is at the point d, comma, f of d. Okay. That's what the extreme value theorem says. Okay. If the function is continuous from x equals a to b, there's some point on the graph where it attains its maximum, the function attains its maximum value, and there's some point on the graph where it attains its minimum value. It's got to happen, okay? Just because of continuity. So f of c is the absolute maximum value. And f of d is the absolute minimum value. All right, any questions on that? All right, theorem 4.14 is known as Fermat's theorem. Fermat's theorem says if the function f has a local maximum or minimum, at x equals c, and if the first derivative at x equals c exists, then f prime at x equals c has to equal 0. Okay. So if we have a local maximum, local minimum, and the derivative exists, it has to equal 0 at x equals c. Okay. So let's do a visual. Here's a graph of an arbitrary function y equals f of x. And I guess I'm actually redrawing this graph over here, okay? But at x equals c, we have a local maximum, okay? And you can see, since that's a smooth curve, right, the tangent line is horizontal, and so f prime of c is equal to 0. We have a local maximum, and the derivative exists, it's got to equal 0. The same is true here at the local minimum at x equals b. The tangent line is horizontal, right? And so we have to have f prime of d is equal to 0. Now the emphasis on this is if the derivative exists, okay? Because, you know, in this type of graph, we have a local maximum, we have a local minimum, but the derivative doesn't exist, does it? Right? So you can't make any conclusions, okay? So if the derivative exists, it's going to be a smooth curve at that point, and the tangent line is going to be horizontal. Okay. All right. And so let's remind ourselves that f prime of c and f prime of d, okay, give the slope of the tangent line. All right. Now I got to give you a caveat, because you can't say the reverse. If the first derivative exists and it's equal to 0, then you have a local maximum or a local minimum. You can't make that conclusion. Okay. Over here, we're saying if you have a local maximum or a local minimum and the derivative exists, then the derivative has to equal 0. Over here, you can't say if the derivative exists and it equals 0, then you have a local maximum or a local minimum. You can't reverse that. Okay. So as an example, let's look at the function f of x equals x to the 5th plus 7. You know how to differentiate that using the basic rules of differentiation. F prime of x is equal to 5x to the 4th. The derivative at x equals 0 is equal to 0, right? It's equal to 5 times 0 to the 4th, which is 0. So in the graph of this function, okay, the slope of the curve at x equals 0, 0. So you might say, well, there's a local maximum or local minimum at x equals 0. But that's not the case. It's a graph of x to the 5th plus 7. Looks something like this. It snakes across the y-axis at y equals 7. But it goes down on the left and up on the right. Okay? So, and I should have drawn this a little flatter. Okay. So the tangent line at x equals 0, right? This is the point 0, 7. The tangent line at x equals 0 is horizontal. Okay? F prime of 0 is equal to 0. The curve flattens out for a moment at x equals 0. So the tangent line is flat. That slope is 0. But there's no local maximum or local minimum there. So F has no local maximum or minimum at x equals 0. Okay. For those of you who had pre-calculus, right, you learned about the cubing function, right? One of those basic functions. So this is x to the fifth, right, has a similar graph to x cubed, right, the cubing function. All right. So far, so good. All right, so let's talk about critical numbers. So this is definition 4.1.6. For those of you who had this in high school, did you guys study critical numbers? What's critical number, Stephanie? Yeah, you were nodding your head up and down. This is your moment of glory.
This was a year ago.
Yeah. Well,
I did do it.
I'm 60, going to be 64. And I was 18 when I learned, right? So that was like 46 years ago. All right. So let's learn what a critical number is. The critical number of a function f is a number c in the domain of f such that f prime, right, the first derivative evaluated at x equals c is equal to 0, or the first derivative at x equals c does not exist. Okay? So critical numbers are all the values of x where the first derivative is equal to 0 or the derivative doesn't exist. So I'm looking at the computer terminal. I guess that we're in the middle of the emergency. Are your cell phones going off? No. So it's going off over here too. All right, so critical numbers, right, would occur at the tops of hills and bottoms of hills, right? Because at the tops of the hills, right, the derivative is equal to 0. Right, the tangent line is, slope of the tangent line is 0. And it would also occur at mountain peaks and mountain valleys, because at mountain peaks and mountain valleys, the derivative is undefined, right? And it would also include this situation over here, okay? Because at x equals 0, the first derivative exists, okay? So that's all we know, okay? Is that a critical number is a value of x where the first derivative is equal to 0 or does not exist. Okay? And we're going to be working a lot with critical numbers between now and the end of the semester. So let's do an example. Okay. Let's do f of x is equal to x cubed minus 3x squared minus 24x plus 92. All right, quiz time. What kind of a function is this? Give me a P. Polynomial. What's the degree? 3, right? This is a polynomial of degree 3. Graphs of polynomials, are there nice smooth curves? Yeah. Okay, nice smooth curves. So to find the critical numbers, okay, for this polynomial function, we first have to find the first derivative. So using the basic rules of differentiation, you can differentiate term by term. Derivative of x cubed is 3x squared. Derivative of minus 3x squared is minus 6x. Derivative of minus 24x is minus 24. And the derivative constant is 0. Right? Differentiate with respect to x. Now we got to find all the values of x that make the first derivative equal to 0. Right? So we set f prime of x equal to 0 and solve for x. So we have 3x squared minus 6x minus 24 is equal to 0. And you will notice that the coefficients are all divisible by 3. So in finding the values of x make this equal to 0, you can either factor it as is, right? Or you can use the quadratic formula, which I don't recommend. So we factor out of 3, and we have 3 times x squared minus 2x minus 8. And now that in parentheses, we can factor. It factors into x minus 4 times x plus 2. Three can, right, now by zero product property, right, 3 can equal 0, but the factor x minus 4 can equal 0, and the factor x plus 2 can equal 0. And so we get x equals 4 is one critical number, and x equals minus 2 is the other critical number. So these are the critical numbers of f over here. So if you evaluate f prime of x at x equals 4, the derivative is equal to 0. If you evaluate f prime of x at x equals minus 2, the derivative is equal to 0. And so since polynomials are smooth curves, we know that at x equals 4, there's either going to be a local maximum or a local minimum. And at x equals minus 2, there's either going to be a local maximum or a local minimum. Okay. Very good. Any questions? So now let's look at the example g of x is equal to the cube root of x. To find the critical numbers, right? This is the cube root function. To find the critical numbers for the cube root function, right? We got to differentiate g of x, and so you know we got to write the cube root of x as x to the 1/3 power. And so now g prime of x is equal to, using the power rule, is equal to 1/3 times x to the minus 2/3. And you know the minus sign means reciprocal. So this is equal to 1/3 times x to the 2/3. And then I can write x to the 2/3. I'll write it over here. I can write x to the 2/3 as the cube root of x squared. Right? When you have x raised to a fraction, the denominator in the fraction is the root, and the numerator in the fraction is the power on the variable x, right? Learn that in pre-calc. We have pre-calc here. Okay. All right. Well, try to evaluate the derivative at x equals 0. You have g prime of 0 is equal to 3. You have g prime of 0 is equal to 1/3 times the cube root of 0 squared. Well, 0 squared is 0, cube root of 0 is 0, and 3 times 0 is 0. So you just end up with 1 divided by 0, which is undefined. So x equals 0, okay, is a critical number of the function g, right? Remember, critical numbers are all the values of x where the first derivative is either equal to 0 or undefined. Okay. And maybe we can figure out why it's undefined at x equals 0. Okay. Here's the cube root function, right? Here's the graph of g of x. You know the graph of the cube root function looks like this, right? Roughly. Okay. Goes through the origin. At the origin, the tangent line is perfectly vertical. And you know that the slope of a vertical line is undefined. And so that's why g prime of 0 is undefined. Okay. So tangent line is vertical at x equals 0. Okay. And a vertical line has an undefined slope. That's why g prime of 0 is undefined. Okay. All right. Any questions on that, ladies and gentlemen? All right, definition 4.1.7 from your textbook. If f has a local maximum or minimum, at C, then C is a critical number of f. And that seems logical. Okay? So let me put up one of our previous graphs. Here's a graph of an arbitrary function f of x, okay? Graph comes down, and then it sharply goes down and to the right, right? So it looks like a parabola plus half of a straight line, okay? And so here at x equals c, we have a local minimum, okay? And the tangent line, right? Slope of the tangent line is 0. So that f prime of c is equal to 0, okay? If f has a local maximum or minimum at c, then c is a critical number of f. So here at x equals c, we have a local minimum, and the derivative is equal to 0. So c, x equals c, is a critical number of that function. Okay. At this point right here, right, that occurs at x equals d, okay? And the derivative at x equals d, right, is undefined. And we have a local maximum here at x equals d, right? So we have a local maximum at x equals d. The first derivative is undefined, and so d has to be a critical number, okay? So we can conclude c and d, okay, are critical numbers of f. All right. The last thing that we have to cover is a scheme, an algorithm, right? A procedure to find the absolute maximum minimum values, okay, of a continuous function on a closed interval, okay? Right, without the graph, okay? So we know how to find the critical numbers, right? Know how to evaluate the function at different values of x. But we aren't going to be able to do it in 6 minutes. So we got this one last section, this one last item from section 4.1, and then you'll have everything you need for the website homework, okay? And it'll be due Monday night, okay? So, because you got your, right? So 4.1 won't be on the quiz, but it'll certainly be on the exam, okay? So I'll see you tomorrow.
Have a good one.